Okay, so we are going to be seeing how the Arnoldi algorithm here it gets modified. Here I've put sort of the main loop, the main outer loop and the main inner loop here. We're going to be looking at how this gets modified under the assumption that A is symmetric. In other words, A is equal to A transpose. Now, as we have seen, for the FOM method to really have a good geometric interpretation, we need A to be equal to A transpose. Now, that doesn't mean FOM doesn't work if A isn't equal to A transpose. It just means the nice interpretation, the nice geometric interpretation does not exist. Okay, so how are things going to change? Well, before I even answer that question, I want to do one computation. So here we define the ij entry of the Hessenberg matrix to be AVJ, the inner product of AVJ with VI. This is a good pattern because what it does, what this shows us, I mentioned this last week, is that essentially the Hessenberg matrix, or not essentially, but the Hessenberg matrix is how we write the action of A on the Krylov space relative to the basis that this is building. Okay, so again, the Hessenberg matrix is the action of A on the Krylov space relative to the basis that we're building. And the whole point is that it is going to be, well, H itself is going to be an M plus 1 by M matrix, and then the matrix that we solve is going to be an M by M matrix, at least for FOM. For GMRes, we're going to solve, there's going to be a least squared problem that we solve with an M plus 1 by M matrix. But in either case, the point is, M is like orders of magnitude smaller than N, the size of A. So A is an N by N matrix, H is an M by M matrix. That is a much easier system to solve, and H is just the action of A on the Krylov space in that, with respect to the basis that this algorithm is building. But what we're going to see is that this Arnoldi algorithm, it actually gets a lot easier when A is symmetric, and it's called the Lanczos algorithm. Lanczos. Lanczos, pronounced Lanczos. That's a Lanczos algorithm. So this is sort of, we're going to see how we can, if A is symmetric, how this modifies the Arnoldi algorithm. But anyways, like I said, the first thing that I want to show is this gives us the entries to the Hessenberg matrix, at least up until I is equal to J. But what about when I is equal to J plus 1? So remember, in each step, we're building the jth column of the Hessenberg matrix, and we go down one entry below the diagonal, and that's what this is right here. And so the question is, does this follow that pattern? In other words, can I write this, is this equal to A Vj, Vj plus 1? Are those two things equal to each other? And what I want to do, first of all, is to show that, yes, they are equal to each other. And it's a simple computation to explain why. So all we're going to do is we're going to write out what this is. We're going to have A Vj, Vj plus 1. Except I'm not going to quite write out what it is. What is Vj plus 1? Vj plus 1 is Wj over the magnitude of Wj. So Vj plus 1 is equal to Wj over its magnitude. So the first thing that we're going to compute is just AVJ Wj. And so actually this quantity right here is going to be this quantity. If you multiply this quantity by the magnitude of Wj, you get this quantity right here. Okay, so now we're just going to simply write out what this is. So, I hope I've given myself enough room here. What is Vj plus 1? What is Wj? Wj is given by this formula right here. Let me just remind you down here what Wj is. Wj is, you start with AVJ, and you subtract off its projection, I equals 1 to j. You subtract off its projection onto the previous vector. So you're going to have A, Vj, Vi, Vi. So this is Wj. It's going to go up here. It's now clear to me that I've not given myself enough room, so I'm just going to move this all down below. Still getting used to the chalk here. All right, so now we're going to have down here AVJ. Okay, and now WJ, as I mentioned, is going to be AVJ. Sorry, my phone is thinking. Let me make this done. Okay. AVJ minus the sum I equals 1 to J A VJ VI VI, like this. Okay, and now we're just going to, the inner product is linear, so it's going to be the inner product of AVJ with this, so AVJ. Okay, and then it's going to be minus the inner product of AVJ with this sum right here. And so when we do that, notice what's going to happen. We're going to, well, let me just write it out. I'm going to write it out in 2 steps. So we're going to have this, using the linearity, this is just a scalar, AVJ VI, and then it's going to be times AVJ VI. So it's going to be times AVJ VI. Okay, so now what we're going to have here, this is the norm of AVJ squared. And notice what we have here. This is going to be AVJ VI squared. Oh, that I should be a J. Like this. Okay. And so now here, whoa, sound a little bit like Peter Brady. AVJ squared, and then minus, what do we have here? Well, this is just by Parseval's theorem, or however you want to look at it, just orthogonality or orthonormality. This is the there's AVJ. This is the norm of the projection of AVJ onto the Krylov subspace that we have computed. Okay, now by orthogonality, since WJ is the part of AVJ that is orthogonal to the Krylov space, this is the part of AVJ that is parallel to the Krylov subspace. By orthogonality, the norm squared of AVJ is equal to the norm of WJ squared plus the norm of its projection squared. So overall, this is the norm of WJ squared. And now, remember, this, let me write it in red. This quantity right here is equal to AVJ VJ plus 1 WJ. So if you look at this and you look at that, this is equal to that. So if you divide this whole equality by WJ, the norm of WJ, that goes away, and this is just a 1. And so what you have is AVJ VJ plus 1 is equal to WJ. So in other words, this is an alternative way to write that formula there. Okay, and that is going to be something that comes into play as we analyze what's happening here. And let me just look here. Okay. So I like using the different colored chalk because it sort of encodes what's happening, gives a visual cue that there's something different going on. But these colors are not always, I for some reason got like dark colors in my chalk set instead of brighter colors. And then the one bright orange color I had, I broke that chalk, or the bright yellow, or the brighter yellow and the brighter orange I had, I broke that. I think I might just look, I have this beautiful box here of chalk, of white chalk. I might just get a box of yellow chalk. Sorry, that has nothing to do with what we're talking about, but stream of consciousness. Okay, so now we're going to see the implications of A being symmetric. In other words, what happens when A is equal to A transpose. So the first thing that we're going to do is we're going to remember that we have this formula, this Arnoldi relationship, Vm transpose A Vm Vm transpose AVM is equal to HM. Remember, H bar is a whole matrix. HM HM is the H bar matrix with the bottom matrix removed. Now A is symmetric. So what is the HM is equal to this? So what about HM? Is HM symmetric? Well, if I take its transpose, it's going to be the transpose of Vm transpose A Vm. And now using the rules of transposes, it's going to be Vm transpose times A transpose, and then times Vm transpose transpose. Okay, Vm transpose, we have that. A transpose, by assumption, A transpose is equal to A, so we just have that. And then anytime you do the transpose twice, you just get back to the original thing. Well, Vm transpose AVM, this is exactly equal to HM. So HM is symmetric as well. If A is symmetric, then H is symmetric. I'm probably going to stop explicitly referring to the M and just say H and V. So if A is symmetric, then H is symmetric as well. Now what does that mean? H is just the Hessenberg matrix that we get from the Arnoldi algorithm. We haven't modified this algorithm yet. So everything we said about the Arnoldi algorithm before is still true. In particular, it is a Hessenberg matrix. In other words, it's diagonal. It has one diagonal below the diagonal, but everything else below that is 0. So what does this mean? Everything below the first subdiagonal is 0. This means everything above the first superdiagonal of this H has to be 0. If H is now, that's the part that requires that A and therefore H be symmetric. So just from the general Arnoldi algorithm, we already know that H is a Hessenberg matrix, meaning everything below the first subdiagonal is going to be equal to 0. So then if we also know in this case that H is symmetric, this means everything above the first superdiagonal has to be equal to 0. In other words, this means that H is tridiagonal. So H is tridiagonal. So I'm just going to write this is tridiagonal. Okay. All right, so now let's work out the implications of that fact. Okay, so now let's work out the implications of that fact. So let's first come over here. So we're going to still do this step. For j equals 1 to m, we're going to do this. We're going to set wj equal to that. But now I want to look at this. Because what we're doing here, remember, we're computing the columns. In each outer loop here, we're computing the columns. Or sorry, not in each inner loop here, we're computing the columns of hj on the outer loop. So if j is equal to 7, we're first going to compute the first entry in column 7, the second entry in column 7, all the way down to the 7th entry in column 7. That's what this inner loop does here. And then after we do that, we compute the 8th entry in column 7. Okay, so one below the diagonal. But if h is tridiagonal, think about what's going to happen. Hij, that is the ij entry, is going to be equal to 0. Okay, so think about j as being fixed. The column j is being fixed. This is going to be equal to 0 if the absolute value of I minus j is greater than 1. Okay, because if we're computing the 7th column, okay, what are the entries in that column that are going to be 0? Well, it's going to be that what are the entries in that column that could possibly be non-zero? Well, it's going to be the entry on the diagonal, that is the 7th row in the 7th column. The entry above it, that's the 6th row in the 7th column, and the entry below it, that's the 8th row in the 7th column. All of the other entries are going to be off of that tridiagonal band that H has. So H is a tridiagonal matrix. So if you pick a column J, the only non-zero entries in column J are going to be corresponding to row J minus 1, row J, and row J plus 1. And this I here is exactly looping through the rows. So Hij is going to be equal to 0 if I minus j is equal to 0. In this loop right here, I is less than or equal to j. So what this means for this loop right here, it's not for I equals 1 to j, it's just I equals j minus 1 and j. For I equals j minus 1 and j. Okay, for I equals j minus 1 and j, we're going to compute these inner products. So for I equals a minus 1 and j, oh, by the way, I have written sort of a classical Gram-Schmidt algorithm here. I haven't combined this step and that one, just because I want to sort of clarify the two different things that are happening. Conceptually, these are sort of two different things. We've got the computation of the coefficients, and then we have the computation of the projections, okay? Mathematically, this and modified Gram-Schmidt are the same, but I think this is a little more clear what's happening. So anyways, so for I equals j minus 1 and j, we're going to compute some coefficients. And you might be thinking that we can use some tridiagonal things to help us here. The answer is at some point yes, but let me just write out what the formulas are, and then we can see how we can make them even easier. Okay, for I equals j minus 1 and j, we're going to say hj minus 1. Okay, so we've got ij, hj minus 1, j. We're going to have a vj and then vi, like this. Sorry, vj minus 1. And then jj is going to be a vj vj. And now what's wj going to be? Wj, okay, so we define wj right here, and this step right here, we're just subtracting off the projection of wj onto the previous vectors. But under this assumption, it is orthogonal to all of the previous vectors except for perhaps the last two. So this is going to be equal to avj minus avj, vj minus 1, vj minus 1, and then minus a vj, vj, vj. Okay. So let me just stand out of the way and let you guys look at that, because I'm going to have to erase a lot of it. Okay, so basically I'm going to erase these two rows and just copy that up there. Okay, so now we see that wj is going to be equal to a vj minus a vj vj minus 1, vj minus 1. I'm about to introduce some notation that's going to make this easier to write. So now I'm just going to have everything crammed in. vj, vj, vj. Okay. This line that I just wrote is just this line copied up there. And then, okay, so let me introduce the notation now. So the notation is that this quantity right here, hj plus 1j, this is called beta j plus 1. So if you have hj plus 1j, the index there goes with whichever of those is largest. It should really either be by the column or by the row, but since it's symmetric, either one is going to work. So the way that bj plus 1 is defined, it's defined as this right here, and the index there matches with the larger of the indices there. Okay, so then what we can do is we can rewrite this a little bit. We can write this part here as avj minus beta j, because if we're looking here, the larger index is j, so beta j, vj minus 1, and then minus a vj, vj. Okay, the other piece of notation that we're going to introduce is that these betas we use these betas when the indices j plus 1 and j are not equal to each other. All right, because h is tridiagonal, these two indices can only differ by 1, and because it's symmetric, hj plus 1j equals hj j plus 1. But we're going to introduce a new sort of similar notation. There's going to be a natural place to put it in just a moment, but alpha j is going to be equal to a vj like this. And so this right here we can write as alpha j. You can write that as alpha j. Okay, so this is what wj is, and then vj plus 1 is simply going to be this divided by its magnitude. So vj plus 1 is going to be equal to wj divided by its magnitude. But here's where some simplifications can come in. What is the magnitude of wj? The magnitude of wj is equal to avj vj plus 1. Okay, so this is going to be equal to wj over the over h j j plus 1 j. So the magnitude of wj, again, why is that? This is just because we're looking at a specific case of the Arnoldi algorithm, and in any Arnoldi algorithm, the magnitude of wj is equal to avj vj plus 1. In the Lanczos case, that is when a is symmetric, this quantity here we're calling beta j. So, all right, what do we have here? This is equal to wj. This is a j here. Is equal to wj. What is this? Well, that's simply going to be beta j. And we've already computed what beta j is. Okay, we computed beta j in the previous step. Here we're working on j plus 1. We computed beta j in the previous step. Okay, so what we're doing, so this now gives us basically the entire Lanczos algorithm. You can see what the difference is going to be. The one of the things that is expressed. So I have expressed everything here in terms of the Arnoldi algorithm, and I've just said here are how the changes. Here's how the assumption that A is symmetric reduces these computations. Notice that instead of doing a whole orthogonalization, we're just doing a partial orthogonalization. It's like with IOM, but here we have a much better basis for doing that. The way that this algorithm is typically presented, I'm going to write, is a little bit different than what we have here, but mathematically it's equivalent. So let me see. Let's see here. So let me erase this. So we're going to have Wj is going to be equal to A Vj minus beta j Vj minus 1, and then minus alpha j Vj, and then Vj plus 1 is going to be equal to Wj divided by beta j. Okay. Now, the modified Lanczos algorithm, it doesn't express it typically like this. Typically, how it gets expressed is the following: Wj is going to be equal to these first two terms right there. So Wj is going to be equal to A Vj minus beta j Vj minus 1. Or that's sort of the Wj that we're going to start with. And then we're going to modify this. We're going to say Wj is equal to Wj minus its projection onto Vj. So it's going to be Wj minus its projection onto Vj. So we're going to have Wj, Vj, Vj. Okay, now why and then Vj plus 1 is defined similarly. Now why are these two things equal to each other? Well, if you imagine taking this and plugging it in here. So if you take this whole thing here and plug it into that Wj, you're going to have AVJ VI, that's the, AVJ Vj. That's going to give you the alpha Vj, but notice Vj plus 1 and Vj are orthogonal. So those are that inner product is going to be equal to 0. At least mathematically, that's going to be what's happening. That's what happens. Now, so that is the Lanczos algorithm. The book has this algorithm sort of spelled out. This is why the algorithm does what it says it does. So he sort of makes an offhand comment. It's surprising that this algorithm does what it does. This is the reason that I just explained here why the algorithm does what it does, because it is just the Arnoldi algorithm in the assumption that A is symmetric, that implies H is symmetric. Since we know that H is Hessenberg, that implies it's tridiagonal. If it's tridiagonal and each entry of H is equal to AVJVI, then most of those entries are going to be equal to 0. So then in the orthogonalization process, what this means is that AVJ is already orthogonal to almost all of the vectors that have come before it. So when we do Gram-Schmidt on AVJ, it's only Vj and Vj minus 1 that it is not orthogonal to, or perhaps not orthogonal to. So the first, vectors 1 through j minus 2, AVJ is already orthogonal to, so you don't have to orthogonalize there. Okay, at least mathematically, it's already orthogonal to vectors V1 through Vj minus 2, so you don't have to do that orthogonalization at all. So you just have to do 2 orthogonalization steps. Now, if you think back to what I said in the introductory video and what I said during the labs, the main time crunch, or the main time suck for this algorithm is in doing this orthogonalization. Now we have just reduced the orthogonalization method to 2 steps rather than, m steps or something like that. So we have drastically reduced the cost of each step. Not necessarily in an asymptotic sense, like the big O thing is still going to be the same, but we have a much better constant now. The other thing that is very important to mention here, and you will explore this in your homework, is that this is not especially numerically stable. The problem is, just like we saw in the lab videos, or just as I mentioned in the lab videos, what can happen? These are floating. All of these computations are done in floating point arithmetic, which means it's not perfect arithmetic. And all of these projections, each time you think you're doing a perfect projection, there's always going to be a little bit of an error. And that error can compound over time until you get the vectors that are not going to be very orthogonal to each other. Now, just in some basic numerical experimentation, I have found that if if the m here is like, so if A is an n by n matrix, and that m is like less than the square root of n, in that case, the vectors do not seem to lose their orthogonality. But once you get past that, the vectors start to lose their orthogonality. I haven't thought very deeply about, whether that is just like an actual thing or just like an empirical thing that I've observed. I think it's just an empirical thing that I've observed. I haven't been able to justify why that would be the case. Anyways, maybe some of you can justify. Like I said, I have not thought much about it, but just in the experimentation that I did and that you will do in your homework, you will see that once you get to a certain point, once m gets big enough relative to n, the vectors start to become non-orthogonal, which means this process is not working anymore. And there are ways of handling that, but sort of the thing that we're going to look at is going to be the conjugate gradient algorithm. But this is an introduction to just kind of all of the good things that can happen if A is symmetric.